Line integrals. In single variable calculus, we talk about integrating along the x-axis. But suppose if we had some function f of xy, and we want to integrate that function along some curve in the plane. If we do this, rather than integrating with respect to x or with respect to y, we could integrate with respect to the arc length of this curve. And so to do this, we would divide up this curve into partitions, and we could look at the value of the function on that partition multiplied by the length of that piece of the curve, and that's what we would have over here. And then if we add all those up and then take the limit as n goes to infinity, we get a definite integral. And this integral here is what we call the line integral of the function f along the curve C, provided that this limit exists. Now, one thing that you might recall from single variable calculus is that if we have a parameterization of this curve, so x is equal to some function of t, let's say, and y is equal to some other function of t, we know that ds is equal to the square root of dx dt squared plus dy dt squared, and then multiplied by dt. We're going to use this result here when we define this integral. So line integrals in the plane are defined to be the integral of some function of x and y along some curve C with respect to the arc length of that curve. Since x and y on the curve can be defined as parametric equations as some functions of t, we can substitute x equals x of t, y equals y of t, and then as I mentioned previously, ds can be expressed as this expression. And so this is the formula for the line integral along a curve C. Now, what does the line integral mean? Well, when you're integrating along a curve like this, you're still plugging values of x and y into your function, which is going to give you some z value. So this is happening in 3 dimensions. And you can think of this f of xy as the height of the curve at any point x and y. And so when you do a line integral, you are finding the area under the function f of xy along the curve. So let's take a look at the following example. We want to evaluate the integral along the curve C of the function 2 plus x squared times y with respect to the arc length ds, where the curve C is the upper half of the unit circle x squared plus y squared is equal to 1. The first thing we need to do is find a parameterization of this curve. So you might remember that to parameterize the circle is actually fairly simple. We're going to simply let x equal to cosine of t and y equal to sine of t, and t is going to be a value starting at 0, which would give us this point, and then we only have to go to pi, and that would trace out half of this circle. So I hope that you remember this parameterization. The parameterization of a circle is something that we use quite frequently, and so it's a good thing to know. Next, we need to find dx dt. dx dt is negative sine of t, and we also need to find dy dt, which is cosine of t. And then we're going to calculate the square root of dx dt quantity squared plus dy dt quantity squared. And this is simply going to be the square root of negative sine of t squared plus cosine of t squared, which is the square root of sine squared of t plus cosine squared of t, which of course is equal to the square root of 1, which is 1. So that's really nice. So now to evaluate this integral, we are simply going to integrate from 0 to pi, because those are the limits of the parameter t that give us the half circle. And then we have the function 2 plus x squared, but x is cosine of t, so that's just going to be cosine squared of t. And then times y, that is sine of t, right, because y equals sine of t. And then times this quantity, but that was just equal to 1, and then dt. And you can see this is a fairly straightforward and simple integral. This is an integral in a single variable. So now we'll just go ahead and find the antiderivative and use the fundamental theorem of calculus. And so the antiderivative here of 2 is 2t. For this portion right here, we need to do a little u substitution. So if I let u equal cosine of t, du is negative sine of t times dt. And so we end up getting negative u squared. Integral of that is going to be negative u cubed over 3. And so we end up getting negative cosine cubed of t divided by 3. And then we're going to evaluate this from 0 to pi. And so we have 2 pi minus cosine cubed of pi divided by 3 minus 0 minus cosine cubed of 0 divided by 3. And this, of course, is 2 pi minus negative 1 to the third divided by 3. And then minus becomes plus 1/3. And finally, we have negative 1/3 here, but a negative. So that's going to be 1/3 plus 1/3 is 2/3. And so we have 2 pi plus 2/3. In the next example, we want to integrate the function 2x along the curve C, where C consists of the arc C1, which is the arc along the parabola y equals x squared from the point 0, 0 to 1, 1. So here is that curve, right? Here's the parabola y equals x squared from 0, 0 to 1, 1, followed by the vertical line segment C2 from 1, 1 to 1, 2. So when you have two curves, we just simply need to integrate this along each of the curves. So we're going to integrate along curve C1, f of xy ds, plus, and then we'll integrate along the curve C2. Okay? The hardest part about doing all of this is just getting the parameterization of the curves. So for the curve C1, how do we parameterize y equals x squared? Well, it's actually very simple. I'm just going to let x be equal to t, and then y would be equal to t squared, right? Those would serve as parametric functions for this parabola. But then we also have to say that we know x is only between 0 and 1, but x is t, and so t has to be in between 0 and 1. So that's the first curve. The second curve is very simple. That's just the straight line segment from the point 1, 1 to the point 1, 2. And for this one, we can see that at any point along this curve, x is always equal to 1. So we're just going to let x be equal to 1. And then y, I'm just going to let that be equal to t. But then we know that the y values are only between y equals 1 and y equals 2. So I'll restrict our t values to be between 1 and 2. So now to integrate the function 2x, along the curve C with respect to s, we are simply going to break that up as the integral along the curve C1 of 2x ds plus the integral along the curve C2 of 2x ds. Now what we need to do is we need to calculate ds for each of the curves C1 and C2. So for C1, dx dt, let's go to C1. C1's right here. Dx dt is just going to be 1. And dy dt is 2t. And so ds is going to be the square root of 1 squared plus 2t quantity squared times dt. And this is the square root of 1 plus 4t squared dt. For curve 2, dx dt is 0 because x is 1. And dy dt is 1. And so ds is going to be the square root of 0 squared plus 1 squared times dt, which is the square root of 1 times dt, which is simply dt. So now to do each one of these, we are simply going to integrate along curve 1. We are going from t equals 0 to t equals 1. The function is 2 times x. X is equal to t. And then we have to multiply by the square root of 1 plus 4t squared dt. Right? So I'm just putting in this ds into here. And then we also need to add to it the integral along c2, which is going to be 2 times x. X is 1 along c2 multiplied by ds, which in this case is just dt. And this goes from t equals 1 to t equals 2 because those are the limits that we imposed on that. So now we just need to do both of these integrations. The first integration is a u substitution. So first of all, let's just change this to 2t. Let's take out those parentheses. And I'm just going to let u equal 1 plus 4t squared. du is 8t dt. So 1/8 du is t times dt, right? So we're going to replace that with 1/8 du. So that integral is going to become 2 times 1/8 integral of u to the 1/2 times du. And if you want, we can even change those limits. So when t is equal to 0, u is going to be 1. And when t is equal to 1, u will be 5. And this is just going to end up being 1/4 times 2/3 u to the 3/2 from 1 to 5. And so we have 1/6 times 5 to the 3/2 minus 1 to the 3/2, or 1/6 times 5 radical 5 minus 1. So that's the value of the first integral. And the second integral, which is right here, I'm sorry, I'm kind of all over the place here, but this integral is simply the integral of 2 with respect to t. So that's just going to be 2t from 1 to 2, and that is 4 minus 2, which is equal to 2. So the total value of this integral, which is this quantity, and this integral, which is this quantity, is simply 1/6 times 5 radical 5 minus 1 plus 2. And we could leave it like that, or we could say 5 radical 5 minus 1 over 6 plus 2, which would be 12 over 6, and we can rewrite this as 5 radical 5 plus 11, all divided by 6. So as an application of line integrals, suppose we have a wire that takes the shape of a semicircle, x squared plus y squared equals 1, so very much like in the first example. And let's suppose this wire is thicker near its base than near the top. And you can kind of see that in the drawing. You can see how the wire is thicker down here and thinner up top. So the question is, find the center of mass of the wire if the linear density at any point is proportional to its distance from the line y equals 1. Okay, let's think about the line y equals 1. Y equals 1 is right here. So if I pick a point on this curve, the distance between y equals 1 and this point, for some random point xy, that distance is simply going to be 1 minus the y coordinate of that point, right? So here's y equals 1, here's y equals y. We're just subtracting 1 minus y. So what we're saying is the linear density is proportional to the distance from that line. So I'm going to find the density, define, as rho of xy. So what is the density at some point xy? Well, it is directly proportional to the distance. Well, the distance is 1 minus y, and so directly proportional just means some constant k multiplied by 1 minus y. Now, the next thing is the parameterization of the curve C here. So the parameterization of the curve C is simply x equals cosine of t, y equals sine of t. T is going to be a value between 0 and pi. And the other thing we need to know is the total mass is the integral along the curve of the density function with respect to the arc length. Okay, so this is just a modification of the formula that we learned in an earlier video about the total mass. So we can calculate this. This is simply going to be the integral of the function rho, which is k times 1 minus y times ds along the curve. This will be k multiplied by the integral from 0 to pi. So now I'm just plugging in my limits here. And then we're going to have 1 minus y, but y is sine of t. And then we have to multiply by ds. Well, we already know that ds is the square root of dx dt squared plus dy dt squared. And in this case, that's going to be the square root of negative sine of t quantity squared plus cosine of t quantity squared. We actually computed this in a previous example. And this is equal to 1 times dt. So we're just going to have a dt there. Now I'm going to go ahead and complete this. We have k multiplied by t minus the integral of sine is negative cosine. And then from 0 to pi. And this is k times pi plus negative 1 minus 0 plus 1. And this gives us k times pi minus 2. So this is the total mass. Now to find the center of mass, well, first of all, let's go back up here. The x-coordinate of the center of mass is clearly x equals 0 because we have symmetry here, okay? There's symmetry in the density on both sides. And so we know the x-coordinate is 0. We don't have to compute that. You can compute it, but we don't have to in this case because we know that's what it is. So the y-coordinate of the center of mass, remember, is 1 over the mass, integral along the curve, and then we have y times rho of xy times ds. And so this will be 1 divided by k times pi minus 2 integral from 0 to pi y, which is sine of t, times 1 minus y, which is 1 minus sine of t, dt, okay? And then don't forget we also have another k in here, right? So we'll pull that out. So I am using the fact that rho of xy is the same function, right? It's k times 1 minus y. And then I'm using the fact that y equals sine of t. So y equals sine of t there, and then the rho function is the same. So we just need to integrate this now, which is a little bit more work. This is going to be 1 divided by pi minus 2 times the integral of sine of t minus sine squared of t dt from 0 to pi. Now to integrate this, of course, we need to use a half angle identity. So we're going to have the integral from 0 to pi, sine of t, and then minus sine squared is 1 minus the cosine of 2t, all divided by 2, dt. So now let's just clean this up a little bit. We have 1 over pi minus 2, integral of sine of t, and then we have minus 1/2. And finally, minus is plus, and there's a 2 down here still, so that's going to be plus 1/2 cosine of 2t dt, 0 to pi. And now we'll go ahead and take the antiderivative of all of these things. So we're going to have negative cosine of t minus 1/2 times t plus 1/2 times 1/2, which is 1/4 sine of 2t from 0 to pi. And now we'll just go ahead and plug in. So when we plug in pi, negative cosine of pi is going to be positive 1. And then we have minus pi over 2. Sine of 2 pi is 0. And when you plug in 0, you get 0 here, and then cosine of 0 is 1, and that's going to be negative 1. So we're going to have minus negative 1. And so, of course, this is 2 minus pi over 2 over pi minus 2. So 1 plus 1 is 2 minus pi over 2 divided by pi minus 2. And you could clean this up by multiplying by 2 on the top and bottom, and that should give us 4 minus pi divided by 2 pi minus 4. And I suppose we could leave it like that. That's the y coordinate. And so the center of mass is going to be the point x equals 0, and then 4 minus pi over 2 pi minus 4. Now let's talk about line integrals along a curve C, but with respect to x or y. So the situation here is, instead of integrating along the curve with respect to the arc length of that little piece of the curve, what if we integrated along the curve, but instead of looking at the arc length here, we looked at the length along the x-axis or along the y-axis? So we can see that the length of the curve here is not necessarily equal to the length along the x-axis, and it's not necessarily equal to the length along the y-axis. And those, of course, are delta x and delta y. So it all works pretty much the same way. If we want to take the integral of a function along a curve with respect to x, we have to have a parameterization for x and y, which we call x of t and y of t. But then we're not multiplying by ds, we're just multiplying by dx. And dx is x prime of t times dt. So it's a little bit simpler of a formula. And similarly for y, if we want to integrate with respect to y, we just have y prime of t times dt. Now, oftentimes we will be interested in adding these two integrals together. And so if I have the integral of some function of x and y, let's say p of xy along a curve with respect to x, and then I want to add to it the integral along the same curve of a different function with respect to y, oftentimes we take the convenience to simply write this in the following manner. Let's take a look at an example. So in this next example, I would like to find the integral along the curve C of the function y squared with respect to x and the function x with respect to y. And I want to do this on two different paths. So I want to do it for the first curve, C1, which is simply the line segment from -5, -3 to 0, 2. So that's this one. And then I want to do it along this other curve, C2, which is defined to be x equals 4 minus y squared from the same 2 points, right? -5, -3 to the point 0, 2. So you can see that we're going from the same initial point to the same terminal point, but one is a straight line and one is a parabolic curve. So the first thing we need to do, let's go ahead and do the first curve, C1. We need to find a parameterization for the line segment that goes from -5, -3 to the point 0, 2. So I showed you how to do this in an earlier video, but I actually like a different method for this. To find that directed line segment from one point to another, all I need to do is find the direction vector for the line. And to do that, I just need to subtract these 2 points. So I take the terminal point minus the initial point. So the point 0, 2 minus the point -5, -3 is actually going to give us 5, 5. So that's the direction vector for the line. And then the parameterization for that line is simply the vector xy has to be equal to, we start with the initial point, which is -5, -3, plus t times the direction vector, which is 5, 5, and then we restrict the values of t to be between 0 and 1. So now if we just simplify this, we get xy is equal to, so adding these together, I have -5 plus 5 times t, so I can write that as 5t minus 5. And then -3 plus 5 times t is 5t minus 3. So my parametric equations are x equals 5t minus 5, y equals 5t minus 3. Now we need to go ahead and compute dx dt, that's going to be 5, and dy dt, that's also going to be 5. And I'm computing these because we need these for each of the respective integrals, right? So the first one, the integral along the curve of y squared dx, is going to be the integral from 0 to 1 of y squared, which is 5t minus 3 quantity squared. And then we have to multiply by dx. Now remember, dx is x prime of t times dt. Or you could think of that as dx dt times dt. So that's just the derivative dx dt, which is 5 multiplied by dt, plus, then we're going to do the second part. Actually, I'll do it separately just to keep that clear. So the second part is the integral, it's right here, of y times dy. Excuse me, x times dy. All right, so x times dy along the curve. This is going to be the integral from 0 to 1 of x, which is 5t minus 5, multiplied by dy dt times dt. Okay, so that's kind of like y prime of t times dt. Y prime of t is also 5 times dt. So I'm basically just going to add those together. So what you can do when you're doing this is you can do one integral. You can have 5t minus 3 squared times 5 plus 5 times 5t minus 5, all with respect to t, right? Because if I just add these two integrals together, I can do it all at once. So now we just have to perform this integration. So let's multiply this out and simplify here. We have the integral from 0 to 1. We're going to have 125t squared minus 150 times t plus 45. So that's what you get when you FOIL this and then multiply by 5. Then we have plus 25 times t minus 25 with respect to t. And let's go ahead and combine here. We have 125t squared minus 150t plus 25t is minus 125 times t. And then we have plus 20 with respect to t. Now we'll do the integration. And of course, all of this should be very straightforward from 0 to 1. And we're going to end up with 125 over 3 minus 125 over 2 plus 20. And this is going to be negative 125 over 6 plus 120 over 6, which is negative 5 over 6. Okay, so now we got to do the second part, which is the same integral, but along C2, which is this other curve. So let's go ahead and get rid of all this work here. And now we have to come up with a parameterization of this curve. Now again, that's not terribly difficult to do. So for curve 2, since x is defined in terms of y, how about I just let y equal t, and then x would simply be 4 minus t squared. And then since y is equal to t, right? And since we want the y values to go from down here, which is at y equals negative 3, to up here, which is y equals 2, we'll just make t vary from negative 3 to 2. And that will give us the parameterization of this parabola from this point down here to this point up here. Okay, so now we just have to perform the integration. So it's very much the same way. So we have the integral along the curve, y squared dx plus x times dy. Let's see if I can do this a little bit cleaner this time. I have the integral from -3 to +2. Y squared is simply going to be t squared times, okay, now we need dx. Now remember, dx is x prime of t dt. And if x is 4 minus t squared, x prime is -2t dt. Okay, and then I have plus, in the second integral, I have x. Well, x is 4 minus t squared times dy. Well, dy, remember, is y prime of t dt. And since y is equal to t, y prime is simply 1 times dt. And so we can do this all in one integral. Let's just clean this up a little bit. We have the integral from -3 to 2. If I multiply this out, I have -2t cubed plus 4 minus t squared, and that is all with respect to t. So it's just basically like I'm factoring out the dt over to the right here. And now we'll go ahead and do the integration. So -2t to the 4th divided by 4 is -t to the 4th over 2 plus 4 times t minus t cubed over 3. And now we're going to evaluate that from -3 to +2. And then we'll go ahead and plug all this in off camera. And the final result here is 245/6. So one thing to kind of note from these two curves is that even though they have the same initial point and the same terminal point, the path that you take matters, right? At least in this example, the path that you take matters. The first answer we got was -5/6, and the second answer was 245/6. So very different results depending on the path. Now let's take a look at the effect on the orientation of a curve and the line integral along that curve. So for example, if we integrate a function f of xy along some curve from a to b, we know that that's going to give us a particular value. But what if we were to go from b to a? What exactly happens when we go from b to a? The easiest way to think about it is when you're integrating, you're going to have some limits for t, which might be something like a and b here. And then you'd have f of x of t, y of t, and then you would have either x prime of t dt or y prime of t dt. But if I switch the orientation of the curve, in essence what I'm doing is I'm switching the limits. And we know that if we switch these limits, a and b, we know this puts a negative on the outside. So the quick answer to this is that if you integrate along the opposite orientation of a curve of a particular function, that is going to give you the opposite value than when you integrate along the sort of positive orientation of that curve. And it doesn't matter if we're talking about line integrals with respect to x, with respect to y, or with respect to s. It all works the same. Line integrals in space. So line integrals in space work exactly the same as line integrals in a plane. The only difference is now you have a function of x, y, and z, and your ds is now a curve in space instead of a curve in a plane. But the formula is the same. It's f of the parameterization of those variables x, y, and z multiplied by ds, and in 3 variables, ds is this quantity here. And we sometimes abbreviate that by calling x of t, y of t, z of t the vector function r of t. So we have f of r of t. And then this right here is the magnitude of the derivative of r of t. And we can also do line integrals along a curve with respect to x, y, or z the same way that we did in the plane. And in this case, we can talk about, an integral of a function of x, y, and z with respect to x, plus an integral of a function of x, y, and z with respect to y, and finally an integral of a function with respect to z. And when we do that, we can combine all of those into a single integral, just as we did in two variables. So in short, it's all very much the same. The one thing that's more challenging, in my opinion, is that the parameterization gets to be a little bit more complicated when you're dealing with a curve in space, because it's harder to visualize and it's harder to draw. So there is a higher degree of complexity with these problems, but mathematically, they are essentially identical. So as an example, suppose we want to integrate along the curve C, where C is this circular helix given by the parametric equations x equals cosine t, y equals sine of t, and z equals t. And so if you graph this curve in space, you can see how it's kind of spiraling and rising all at the same time. Okay, and that's called a helix. And t is between 0 and 2 pi. So this problem is really not that tough because they gave us the parameterization of the curve. So all we have to do here is calculate ds. ds, of course, is the square root of dx dt squared plus dy dt squared plus dz dt squared dt. So let's go ahead and do this. dx dt, the derivative of cosine of t is negative sine of t. dy dt is the derivative of sine of t, which is cosine of t. And dz dt is the derivative of t, which is 1. And so ds is going to be the square root of negative sine of t, quantity squared, plus cosine of t, quantity squared, plus 1 squared. But this is the square root of 2, right? Because this is sine squared plus cosine squared, which is 1, and 1 plus 1 is 2. So we have radical 2 dt. So now the integral along the curve C of the function y times the sine of z ds will be the integral from 0 to 2 pi. Y is the function sine of t, multiplied by sine of z, which is sine of t as well, because z equals t, multiplied by ds, which is radical 2 times dt. And so this becomes radical 2 integral of sine squared of t dt from 0 to 2 pi. Now we'll just go ahead and apply the half angle identity. We'll factor out the 1/2 and we'll integrate. And I hope you follow all this work here. This is good old calculus 2 stuff here. And of course, the integral of 1 is t, not 1. There we go. And now when we plug in 2 pi and 0, we simply get radical 2 over 2 times 2 pi, which is pi times the square root of 2. In our next example, we want to evaluate the integral along the curve C of y dx plus z dy plus x dz, where C consists of the line segment C1 from this point 2, 0, 0 to the point 3, 4, 5, followed by the vertical line segment C2 from 3, 4, 5 to 3, 4, 0. Okay, the hardest part in this problem is just finding the parameterization of the curves C1 and C2. But it works exactly the same as it did in two variables. So since we're talking about a line segment from 2, 0, 0 to 3, 4, 5, first I'm going to find the direction vector for that line, which I can get by subtracting 2, 0, 0 from 3, 4, 5. So that's going to give us 1, 4, 5. And you know what? We'll go ahead and do the direction vector for the other line, which is from 3, 4, 5 to 3, 4, 0. And to get that one, we are going to subtract 3, 4, 5 from 3, 4, 0. So 3 minus 3 is 0, 4 minus 4 is 0, and 0 minus 5 is negative 5. So we should have 0, 0, negative 5. And then the parameterization of each of these curves, x, y, z, you start with the initial point written as a vector, which is 2, 0, 0, plus t times the direction vector, which in this case is 1, 4, 5, and t is between 0 and 1. And we can rewrite this as t plus 2, 4t, and 5t, right? That's just multiplying the t through and then adding these points here. Okay, the parameterization for the second curve, very similar. We're going to say it is x, y, z equals the initial point, which is now 3, 4, 5, plus t times the direction vector, which is 0, 0, negative 5. And again, t is between 0 and 1. And that's okay for these to have the same values for t because we're going to do two separate integrals anyway. And if I simplify this, we're going to get 3, 4, and then negative 5t plus 5. So now we have the parameterization of each one of those. So to do the integral along the curve c of y dx plus z dy plus x dz, we are essentially going to do this integral twice. Once for C1 and once for C2. There we go. All right, so now let's go ahead and do this. So the first integral, which I'll do here in blue, is going along this curve, this parameterization from 0 to 1. We have y times dx. Y is 4t. dx is x prime of t times dt. X prime of t is 1. Let's go ahead and do y prime and z prime while we're at it. Y prime is 4 and z prime is 5. So it's going to be 4t multiplied by 1 dt plus z, which is 5t, multiplied by dy, which is y prime of t dt. So that's going to be 4 times dt, plus x dz, which is t plus 2. dz is 5 dt. That's the first integral. And then we're going to add to that the second integral, which is this one here. And that's going to be the integral also from 0 to 1 of y, but now we're looking at these ones here. So y dx is going to be 4 times, and then what is dx? Well, x prime of t is actually 0. Y prime of t is also 0, and z prime of t is negative 5. So we're actually going to get 4 multiplied by 0 dt, which of course is 0, plus z, which is negative 5t plus 5, multiplied by dy, which is x prime of t dt, which is also 0, plus x times dz, which is 3 times negative 5 times dt. So that's 0, that's 0. We can ignore those, and now we can just focus in on the rest of this. So I have the integral from 0 to 1. I've got 4t plus 20t plus, right here I have 5t plus 10 dt plus the integral from 0 to 1 of, what do I have here? Negative 15 dt. Okay, now we could do a little bit more combining here. I think it's worth it to do this. I have 29t plus 10 dt, and then this one actually turns out to be minus 15 integral of dt. Okay, so now let's do it. We have 29t squared divided by 2 plus 10t from 0 to 1, and then minus 15t from 0 to 1. And so we have 29 over 2 plus 10 minus 15 times 1. Let me do that in green. Right, because when you plug in 0, you get 0. And this is all equal to 29 over 2 minus 5, which is 10 over 2, which ends up being 19 over 2. So again, I think the hardest part of this problem And it's not really hard, but the most time-consuming part of the problem is in the beginning when you have to find the parameterization of the curve. The rest is pretty much just using a formula and plugging it in. Now let's take a look at line integrals of vector fields. And this is going to have an application to work. So imagine we have some curve in three-dimensional space, and within that space we have a function that defines some vector field in that space. So at any point on this curve, there will be a vector from this vector field associated with that point, right? So at a point right here, we have a particular vector that is given from that vector field. How do we define the integral of the function along that curve? We define this to be the integral of the dot product of the vector field function with dr, where r of t is simply the curve C written as a vector function. So this is the integral from a to b of the vector function of r of t, dot product with r prime of t times dt. Now, if we use a unit tangent vector here, we can change this into the dot product of the vector function, the vector field function with the unit tangent vector multiplied by ds, which of course is the arc length. Let's do an example. Find the work done by the force field F of xy is equal to x squared times I minus xy times j, and moving a particle along the quarter circle, r of t equals cosine of t times I plus sine of t times j from 0 to pi over 2. So what we're doing is we're moving a particle along this quarter circle, starting here, moving up to here, and all the while we have this force field acting upon that object in the directions that you can see here. So as we're moving along here, we have this force kind of acting against that point, and we want to know how much work would be done traveling from one to the other. So first thing I'm going to do is I'm going to write f of xy in the format that I like to use, which is going to be x squared and then negative xy, right? So instead of using the I and j notation, I prefer to do this. Now r of t, also we can write that as cosine of t, sine of t. This should be no surprise because we are talking about a circle, right? This is the same as saying x equals cosine of t and y equals sine of t, right? And we're going from 0 to pi over 2 because we only want a quarter of the circle. So definition here is that the work done is going to be the integral along the curve C of f dot with dr. This is going to be the integral from 0 to pi over 2 f of r of t dot product with r prime of t dt. So what we need to do here is we need to calculate r prime of t. So r prime of t is basically just a vector valued function here where we take the derivative of each of these components here with respect to t. So that is negative sine of t and cosine of t. And then f of r of t is f of, so I'm going to do this right here, f of r of t, which is cosine of t sine of t. And that just means we're going to let x equal cosine of t and y equal sine of t. Now, f is right here. F of xy is x squared. So if x is cosine of t, that's going to be cosine squared of t. And then y is negative x times y, but if x is cosine of t and if y is sine of t, that's negative cosine t times sine of t, which I'll represent as negative sine of t cosine of t. And so now we just have to take the dot product of this, and then perform the integral. So we have the integral from 0 to pi over 2. We have cosine squared t negative sine of t cosine of t dot product with negative sine of t cosine of t dt. Now remember how dot product works. All we have to do here is multiply the x components, so cosine of t times negative sine of t is negative cosine, it's cosine squared of t. So negative cosine squared of t sine of t. And then we have plus this times this, which is going to be minus sine of t times cosine squared. Oh, how convenient. It's the same thing, right? dt. So that's going to be negative 2 of those. All right, and then this is a simple u substitution problem. So if I let u equal cosine of t, du is negative sine of t dt. And we actually have a negative out here that will serve that function. And so we're going to end up getting 2 times the integral of u squared du. And cosine of 0 is 1, and cosine of pi over 2 is 0. And so this is going to be 2u cubed over 3 from 1 to 0, which is 0 minus 2/3, or negative 2/3. Now let's briefly talk about the connection between line integrals of vector fields and line integrals of scalar fields. So if we have a line integral of a vector field over some curve C, we define that to be the integral of f dot product with dr, which is equal to this. This is the example that we just did a second ago. But if we think of f as being some function p times I plus q times j plus r times k, we can think of f of r of t as simply being p, q, and r. And then we're going to take the dot product with r prime. R prime is x prime of t times I plus y prime of t times j plus z prime of t times k. And that dot product is simply going to be p of x, y, and z multiplied by x prime of t, and then q of x, y, and z multiplied by y prime of t, and r of x, y, and z multiplied by z prime of t, all with respect to t. But we can use the alternative notation if we multiply dt through to each one of these. Remember, x prime of t times dt can be represented by dx. And so we can simply say that it's p times dx, q times dy, and r times dz. So when we integrate along a curve of a vector field, we can think of it in this manner, which is really, really convenient. And that concludes this video lesson.